Next up, we have Praveen and Chango from Samsung, and they will actually talk about how they tuned RocksDB, used one of our or many of our configuration parameters to improve their RocksDB performance. Awesome. There you go.
Good evening, one and all. I'm Praveen Krishnamurthy from I'm Praveen Krishnamurthy from Samsung Semiconductor Inc. So I'm part of the team which basically optimizes the I/O stack for SSDs. So today's talk that I'm going to deliver is to share our experience of how we used RocksDB and how we basically improved the performance for our use cases. So we work on like features like multi-streaming, that is basically trying to categorize data which are together within the SSD at the same eraser block size. So that is one of the feature that we worked on. So for such features, what we try to do is once we implement that, we try to identify what is the performance improvement that we are getting out of it. Not only performance improvement, but also the SSD, NAND flash, endurability data. So, and also we also work on like NVMe SSD, which is PM 1725. So we try to optimize it for higher performance. So as we started working on it, we tried to identify some applications which can make use of the speed that NVMe SSDs could deliver. So that's where our RocksDB usage comes in. So we use RocksDB to basically identify what performance we could obtain from this. So so as we started using RocksDB, we figured out that it contains like around 120 configurable parameters, and the default parameters does not seem to squeeze out the maximum performance out of the high-end NVMe SSDs. And then we started looking into the RocksDB developer forums and then started obtaining values what could be used for these configuration parameters. And then we wanted to identify what values are best for the workload and the environment that we have. So that's where it all started. Okay. Before delving into the exact procedure of how we did this, so this is our system details. So it is a dual socketed server with Intel Xeon and contains 16 physical CPUs, and we were using Linux. And the NVMe that we used, NVMe SSD that we used in question was PM 1725, and the other NVMe SSD which we used is basically for backing up the data set. Basically, the data set we used to copy from there to the 1725. And the file system that we used was XFS file system, and then the benchmark tool that we used is dbbench. So the data set size we created is around 253 gigabytes. So we created this using dbbench itself, using fill sequential and followed by an override, so that we have all the key value pairs which are like random. And then we also kept it in such a manner that it is in a 1:4 ratio. That is like the RAM size is like 64 GB and the data set size is around 253 gigabytes. And the key size is 16 bytes, and then the value size is 800 bytes, and the operation count that we had set it is at 500 million operation count. And the different workloads that we tried to optimize the values for are 80% read and 20% write, with and without compression. And when I say compression, we used snappy compression for the level uh, thing, and also 50-50 read and write with and without snappy compression. So the procedure is the benchmark procedure that we followed is this. We basically identified around 25 configuration parameters and then started as having some set of values, say for example 4 to 5 values for each of those parameters. if we take the block size into consideration, we chose some 5 values like 2K, 4K, 8K, and 32K. And then at a single time, we set one parameter. We used to pin one parameter, and then the value for that parameter we would basically vary. We would vary from 2K to 4K and 8K. For each value, we would try to run an experiment of running the benchmark for 500 million operations, and then arrive at the value for arrive at the performance results. And initially we started off, so the values that we started off with is not exactly the default values. We started off with the values which we obtained from the forums, and once we started with that, we performed this benchmark operation. And once we figured out one parameter value, which is the optimal value, we will provide that as a feedback to the next one. When we move on from block size to the write buffer size, we would use the optimal value for the block size. This is very similar to a greedy algorithmic approach. So this is some workload data that we have. Like for a 50/50 snappy workload, we started off with block size, which contains multiple values, 2K, 4K, 8K, 16K, and 32K. And we identified as we ran our experiments that 8K gave the best results for that in our setup. And the basic idea is to obtain something like a bell curve. So the graph that you see on the right is more like a normalized operations per second data. And so that's the reason we selected 8K for this. Similarly, we did this for around 25, 24 parameters. So this list is basically a set of for different workloads, something like 80/20 snappy, 80/20 uncompressed, 50/50 with snappy, and 50/50 uncompressed. So the baseline values that you see, the second column is the baseline values. That is the values we started with, and then we moved on to the. Uh, so as we ran the experiment, we figured out that the green blocks indicates that the value basically deviated from the baseline value. So this is the set of values, and these are all, this is just a continuation of the previous slide with different configuration parameters. And then coming on to the performance comparison chart, we were able to realize in the best case, like for 80% read and 20% write with snappy compression, we were able to see an performance improvement of 76.79%. And similarly for read, the 80% read and 20% write with uncompressed, and so on and so forth. So our idea is to basically use these parameters for our experiments, parameter values for our experiments, and then see how much we are able to delineate one performance from the other. And obviously, because this is a greedy algorithmic approach, we might obviously miss the global optimal value, and we would obtain only the local optimal value. And this we thought is more like a good start off point. But as we start using the database, as we monitor the data, the key value logs, we would get to know like what other changes we need to make. But we thought this is a good start off point. And most of you would know more about performance tuning. So I would like to hear your comments and feedbacks as well, so that it's more like a two-way conversation. Thank you. Yeah, right. So the question is basically, does multi-stream can be used on all of the Samsung SSDs, right? Right, right, right. This this is not the multi-streams track. This is just plain Samsung SSD. Right, 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 right. Yeah. Um, right, right. So basically, when we do the first thing, like when we run for 2K, 4K. So in the next slide. Okay. So let's compare block size and write buffer size. So when we ran with block size 4K, the write buffer size was 256. So as we move on, as we selected 8K after the experiment, when we move on to the write buffer size, we still run with 256, 512 and everything. But we don't try with 4K again because that would lead on to a exponential set of runs that we need to do. Yeah, yeah, that's why. So basically, when we move on from the block size to the write buffer size, the block size is set at 8K. We don't try for 4K or 16K. So does that answer your question or? Okay. Yeah, yeah. Each has a separate values. Like, yeah, no, yeah, no. Uh, yeah, we looked at the IOStat data. So still we were not able to reach the 100% of the IOStat utilization. We were seeing around 80 percentage, but more than the SSD utilization, we were not able to use the CPU. The CPU utilization was mostly at 40 to 50 percentage. IOPS. Okay, the IOPS that we saw, this is basically for 80 with snappy compression enabled. So the operation count is for 500 million operations. So it's not a big thing. So we were seeing something around for the not for the baseline, we were seeing around 174K. And then for the optimized, we were seeing around 316K. But but the experiment basically ran for probably 30 minutes to 1 hour because that's the. But as the time goes off, you would see a dip in the performance. So yeah. The garbage collection will kick in within the SSD, and also yeah, the compactions, because before each experiment we secure erase the SSD so that we want to make sure that garbage collection within the SSD does not play a role in this experiment, because this is not specific to any SSD. We want to make sure that we are actually trying to monitor the RocksDB configuration parameters. Yeah. Uh, these are the basically this is the DB bench operations per second value. Average. Yeah. We didn't actually graph this for our only metric that we took into consideration is operations per second. We did not uh, look for the P99 latency. No, not for the steady state, because we wanted to, this is more like a side project. We wanted to do it as soon as possible. So we wanted to arrive at some values to start with, and then over the period of time, we can tweak it according to our need. So that's the reason we did not let garbage collection value affect these. Yeah, yeah, that is true. That maybe. So basically, I read through some of the forum discussions, and then we arrived at, okay, let's start with block size seems to be the most, it's more like guess methodology. There is no specific that's what we did. But it's more like we started off with, so it is basically in this order we tried out. So it is exactly in this order how we did that. Yeah, right. So we use something like a poor man profiler. We were looking, basically I was using RocksDB 3.11 version. So there were some mutex lock or something which was, but we did not delve deep into what is causing that. But yeah, so it's basically, we thought it is something to do at the software layer. Yeah. So each value, we basically run it for 500 million operations. So that would take around, depending upon what load it is, it will take somewhere between 30 minutes for, so basically the optimized, so the 80/20 snappy compression, the optimized one would basically finish off in 30 minutes. But with the baseline, it would take around 1 hour or something. Yeah. Right, 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 right. Yeah, like you said, so that's where we need to monitor the performance over time, and then tweak the level zero slowdown rate, and then level zero stop rate. Yeah, yeah. Okay, okay. So basically, for say for example, for block size, we ran 5 experiments. 5 experiments for each one, like 2K, 4K, 8K, 16K, and 32K. Yeah. Yeah, basically, the first experiment that I did was with 50/50 snap, 50/50 uncompressed, 50/50 uncompressed. To make sure that this is consistent, I ran the test twice. I was able ran the test twice for both the baseline values and also the optimized values. The difference wasn't much, probably 1% or 2%, not more than that. And I ran it on 2 different SSDs as well. Yeah. No, I didn't do that. Initially, I fixed it this way, and then I stuck with it. Yeah. Yeah, I think we are at the end of this session. Thank you. Thanks.